There are three main design advantages to using National Semiconductor's power modules: best-in-class thermal performance, low EMI, and ease of use. In front of me is the evaluation board for the LMZ12003 module, which is rated for a maximum input voltage of 20 volts, 1.8 volts out at 3 amps. This has been connected to a load for at least an hour, an ambient temperature of about 25 degrees C, with no forced air cooling. I have a thermocouple connected to the exposed pad on the bottom of the IC. The temperature is about 32 degrees C, and the temperature of the top of the case is about 31 degrees C, below what one would expect for such a compact solution. Both the efficiency of the IC and the theta JA rating of 20 degrees C per watt is quite an improvement compared to a switcher in a similarly rated discrete solution, which would commonly have a theta JA of 2 times degrees C per watt. Keep in mind, there are additional data of these power modules in higher temperature environments, like 85 degrees C ambient. Another advantage that Martin mentioned is the low EMI of National's power modules. Having a shielded inductor encapsulated in the innovative packaging is ideal for noise-sensitive applications. These evaluation boards were placed in an anechoic chamber and tested to CISPR 22 Class B radiated emission limits. Testing was done according to the CISPR radiated emissions test setup, with the power module evaluation board as the equipment under test, mounted both vertically and horizontally. Shown here is data pertaining to the LMZ14203, tested for a 24 volt to 3.3 volt conversion at 3 amps. As the test data shows, the EMI signature of the power module is below the limits of EN 55022, the emissions testing standard for information technology equipment. The third differentiator of National's power module is the ease of design. The power modules are available on Power Webbench, National Semiconductor's online tool that allows me to easily create a power design by entering my input and output voltages and current requirements. By going to the Aero NAC website, I can use the Power Webbench and create my power designs using Aero components. Instead of wanting 20 volt input, 1.8 volts out, and 3 amps, I'd like to have 36 volt input, 3 volts out at 2.65 amps. This Aero version of Power Webbench will provide me with all the solutions that meet my requirements. And by going into the new Webbench visualizer, I can quickly compare the different solutions using filters such as efficiency, footprint, BOM cost, BOM count, and other meaningful parameters, as well as which features I want to include. For my new design, I've chosen to use the 42 volt input power module, which is pin compatible to the 20 volt module currently installed on the evaluation board. Because so much is integrated in the module design, no layout change is needed, and I can use the same printed circuit board. And the simple packaging of the device affords me the ability to do the rework myself using common lab tools, such as a heat plate, some flux, and a tweezer. I've set my heat plate to 260 degrees centigrade, and I'm placing my eval board on top of it. I actually like to use solder paste and just kind of put it on the corner of one of the copper, just to make sure I know when that has reflowed, because to me that means that there's reflow and the board is hot enough where I can lift off the part. So I see that the solder paste has reflowed, which is a sign that I can gently remove the component. And here's the 42 volt part. It goes into the same layout. What I'll do is add a little bit of flux. So after a few minutes of changing just a few components, I have a new power design. Instead of an input voltage of 20 volts, my new design has an input voltage of 36 volts. And my output voltage has changed from 1.65 volts to 3 volts.